Hello there, Physics 30. Welcome to Chapter 16, Lesson 2. We're on atomic physics. We're going into nuclear decay. So what you just read in your anticipation guide will have a bunch of calculations for energy of fusion and fission. We're going to cover that a little bit later. That'll be in Lesson 4. But this is just more talking about the different types of nuclear reaction, or not, sorry, nuclear decay. All right. Nuclear decay comes from the idea that we have a nucleus that is going to decay, right? Which means it has a nucleus that's going to decay, which means it's going to start as a larger nucleus generally, right? These are going to start with lots of protons and neutrons. They're going to work their way down to a more stable isotope, all right, more stable nuclei, right? Okay. So there are three types: alpha, beta, and gamma, and usually it comes down to balancing. All right. So what we're going to talk about here is that we have concentration charge and concentration in nucleons, right? So the bottom number has to be always add to the top number. So when we're doing these, what's important is when we have these numbers, they always add up. Okay, and this is talking about the numbers that are on our elements. All right. So first thing, let's just talk about what makes the difference between nuclear decay types. So what we have alpha particles, beta particles, and gamma rays. Alpha particles, they're the lowest penetrating ability. They're helium, okay, particles coming off. They happen quite often, all right? They happen quite often. Their ionization is high, but their hazard's really low. It's not really going to generally affect you if you're hit by this. You're hit by this every day. Okay, then you have beta. All right, now they can travel 30 to 50 centimeters in air, and they penetrate about 1 centimeter into the body. They have a moderate level of ionization, but they're also low risk. Where we get this idea of nuclear reactions poisoning people and radioactivity killing us and all that stuff, that generally is coming from gamma rays. Now remember, gamma rays, you think about your electromagnetic spectrum, right? All the way from there here, they're at this end. They're at the high energy end. All right. They can travel a long ways through air. They're very powerful, very high energy. They have a low ionization, which means it just doesn't happen as much. It also means that they don't really interact a ton, but when they do, they're extremely hazardous. They're really highly hazardous, right? And so there's kind of this idea that we have an alpha particle will react is a positive particle, beta is negative, and a gamma is a photon, so it doesn't react in the magnetic field very much. All right. So, why elements decay? Well, the reason is that what we have is we have two types of forces getting involved in the nucleus, right? And we've shown this before. Is we have our protons, right? We have some neutrons, all this kind of stuff. Now, as long as they're within this circle, right? This is where the strong nuclear force, okay? It's not Sunday Night Football. That's a strong nuclear force. The strong nuclear force can overpower, right? And it does the electrostatic, right? So the strong nuclear force is winning in this case, as long as we're within something that size. What happens is when we get larger and larger elements, we're adding more protons and neutrons. We take that same circle, except for now, instead of 2 protons and 2 neutrons, we've got, a few hundred packed into that kind of circle. Remember that we're drawing something two-dimensional. Right, we've got a few hundred, and sometimes we actually end up going slightly just outside that circle. So when elements get to a certain size, they actually end up outside that circle. Now, when they're outside that circle, that means that they're considered unstable. They're unstable, right? So this is kind of that. This is kind of where that circle is, somewhere in here, right? And so now they're unstable, and since they're unstable, they want to rearrange. But in order to rearrange, they have to get rid of stuff. So what they're going to do is they're going to say, okay, well, this one's the farthest out, and it's being rejected, and this one. And so what we're going to do is we're actually going to shoot this piece off. And by doing that, when we shoot that piece off, it's going to create more room for the other pieces to rearrange and go into that. And that's kind of what alpha decay is, all right? So that's one of the main ones. Okay, and that's just because the electrostatic force kind of causes that, more or less. All right. So that's the general reason for alpha decay. Beta decay is caused more by the weak nuclear force, which is super complex, and it's the idea of like an up quark turning into a down quark or a down quark turning into an up quark, which is a relatively not well understood concept. All right. So this is happening, right? We've already talked about this. And so things kind of get together. And so we have beta particles come off the nucleus or gamma rays, all that kind of stuff. So we're going to start with types of radiation. All right. So the first one is we have parent, daughter, alpha, and gamma. Now, gamma generally is not what we're going to use. We're going to consider just energy. Sometimes it is a type of gamma ray, but it's generally just energy. All right, the parent is what was originally, so it was the original nuclei. The daughter is what the new nuclei is, and the alpha. So you're going to use your periodic table sometimes to kind of predict what's going on as well. Okay, so this won't work on your Chromebook as far as I remember. Okay, but you can try it on if you have a home computer. Try that, check it out. All right. So what we're going to have here is we have the plutonium here, right? And it's decaying into uranium and an alpha particle. So when we go to write this, we have an example of the equation for alpha decay of plutonium. So we start with plutonium, that's the parent, that's what it originally was. Its daughter is the one. So you notice that the top numbers, the 240, 236, and 4 have to balance out, right? So when I give an alpha particle is 4 in total and 2 protons, right? So the 4 in total is telling me that it is 2 protons, 2 neutrons, and there's 2 protons involved. And these have to balance. So 240 on this side has to remain. Like we can't just disappear like neutrons and protons. They have to all stay the same. So 240, and then it goes to 236 and 4. 236 plus 4 equals 240. So that's how I knew that this uranium is a 236. It also goes, plutonium goes down to 92, and it's got a 2 here. So the top is conservation of nuclei, how many nuclei they are, and the bottom is conservation of charge. This has a positive charge of 94, and this side has a positive charge of 94. All right, when you're writing out alpha decay, you can write the alpha symbol, or you can write helium. Either one is acceptable. Okay, this one here, predict the daughter element, the results of alpha decay of radium-226. So radium-226, I have to kind of figure this out. This is going to come from a periodic table. So I'm going to go to my periodic table here, okay? And I'm going to find radium, all right? Radium is number 88, kind of bottom left-hand corner. Sorry, I can't use my little writer here. Radium, bottom left-hand corner, right to the right of francium, it's number 88. So I know it's in number 88. So I can write radium 88 and go from here, right? So it's radium 88. And then I know it's going through alpha decay, so it's going to reproduce this, right? And by using this, okay, well, this is 226. I'll show you guys what I did, I guess, right? So if this is 226 and I'm losing 4, I know this has to be a 222, right? And since this is 88 and this is 2, I know this has to be 86. All right, this has to be 86. Now I have to, in order to find what element 86 is, right, where the Rn comes from, I go back to my periodic table, and I find the element number 86. Well, element number 86 is on the right-hand side. It is radon. Okay, and so how this kind of works is that I'm actually going from the 7th line to the 6th line. I'm working my way down the periodic table. Okay, and that's an important thing because what that does is that the lower we are in the periodic table, right? So anything lower than iron, iron's number 26, is stable. Stable, anything 26 or lower is really stable, right? Even up to zinc's pretty stable and stuff like that, but iron is considered one of the more stable elements. Okay, so radon and radium are really far away from that. So their goal is to work, radium wants to decay back all the way to iron. And so by doing this alpha decay, we're going to work our way down this periodic table and eventually get to iron. Okay, and that doesn't happen very quickly, but it can happen. All right. So radium was number 88, and now radon is number 86. Did I put the right letters there? Yeah, Rn. Okay. So one thing to keep in mind is that momentum and energy are conserved during the decay process. If the initial element was at rest, the daughter nucleus and alpha particle must have equal amounts of momentum. And so when we have equal amounts of momentum, we can conclude about the two speeds. And so if we think about it, the weight of this, right, is so much higher. I don't want that. The weight of this is so much higher than this, that it's going to have a very small speed, and the helium's going to have lots, right? So most of the kinetic energy will go to the helium, and that's just kind of something you can break down as we go. Okay, so most decay goes to the alpha particle. All right, so now we're going to beta decay. Beta decay is due to the work weak nuclear force. It doesn't have so much to do with electrostatic. All right, and what it is that a neutron just decides, and this literally decides is the best way I can describe this, that it wants to be a proton. Well, in order for a neutron to turn into a proton, it's got to fire off an electron. And of course, we have this little guy. Do you guys remember what that thing's called? Yeah, that's a neutrino. All right. That's a neutrino. It's actually an anti-neutrino, but yeah, it's a neutrino. And so we have a neutron turning into a proton, and an electron, and a neutrino, right? So this is what, remember, we knew that there was a neutrino, and we already talked about this during class because of momentum. Okay, so elemental neutrinos, basically they're predicted to have existence due to the momentum. They also have there's really no like discovery until 1956. Okay, and then we kind of figure out, holy man, like these are a big part of the universe. So the Earth is showered with billions of neutrinos from the sun for every centimeter squared of area. Super clean detectors deep underground, as shown, allow the occasional neutrino detected. So if I zoom in here, this is deep underground. So the underground here, this is kind of the deal. What you can see is this is water, almost perfectly still water, and then it's surrounded by thousands of detectors up here. These are all detectors, okay? And so what's happening is they're actually having a neutrino comes in. It's supposed to interact with the water, which doesn't happen very often, but it does. And then these detect when it interacts with the water, what it gives off. So these are so deep underground that nothing else can get to it except neutrinos. And they're very, very massive, massive investments just to detect these things, okay? Yeah. All right, so electron has a very small mass. It's going to a tiny fraction of atomic matter, so the mass of the nuclei is not really changed. So we say the mass number remains unchanged. So what we're going to say is that the top has to still balance out, and the bottom still has to balance out. So even though we're taking some mass away from the nuclei, because right, we're not going to say that it still is zero and electron zero. So we have a 1 over 0, and so our tops have to add to 1, right, which they do. Proton counts as a 1, electron counts as 0. Okay, we're generally going to use this B instead of electron, just because there's an opposite of a B, which is a positron, right? And then our bottoms have to add a 0. I have 1 and negative 1, so that still works. And of course, we're going to have this V is a symbol used for neutrino, and that bar means it's an anti-neutrino, okay? So that is the idea of beta negative decay. We can also have beta positive decay, which is where a proton just decides that it wants to be a neutron, right? And what it gives off is it gives off something called a positron, which is the antiparticle of the electron. All right, so that there's some interesting concepts there. So positron is the antiparticle electron. What it means is that it is identical except for one key feature. For example, the positron is the positive charge of an electron. Same mass, same everything else, but the positive charge of it. And so we can say the same thing. So again, the tops and bottoms do that. So the proton decides it wants to become a neutron, and then it gives off a positron, which is a small amount, has a very small mass, but a positive charge. And so you get this one on top and 1 on bottom, right? Okay, we call this beta positive decay, and we give off a neutrino. So beta negative gives off an antineutrino, beta positive gives off a neutrino. Something I'm probably not going to be a stickler on if you missed that. Okay, so positrons and antiprotons, they have what's called transitory existences. What that means is that when you do create a positron, for example, it's going to come into contact with an electron very quickly. When a positron and an electron hit each other, since they're all antiparticles of each other, they instantly annihilate. Okay, they annihilate, which means they destroy, they leave existence. All right. Why they do this, it's kind of confusing. It's about, it's the equivalence of if you ever meet your evil twin, you'd want to destroy it, I guess. right? And that's kind of what happens with protons and or positrons and electrons, right? They are opposites, so when opposites hit each other, they destroy each other, right? Same as how if you have a +1 and a -1, they kind of cancel each other out, right? And that's, yeah. All right, so you can kind of again try this one on your Chromebook, or try it on a home computer if you got one. Okay. If you want to know what signs and stuff like that, okay, the electron, positron, electron, neutrino, antineutrino, these are kind of give you a little bit of an idea of like charges and masses and that kind of stuff, and go from there. All right. So I'll write the equations for beta negative and beta positive decay of carbon 14. So what I started with is I started with carbon 14 here, right? Carbon 14, and I'm going to do beta negative. Okay, beta negative looks like that. So if I do beta negative, okay, and that's my antineutrino, then I can look at the conservation of nucleons. So that's the top number. So if I look, I have 14 on the left and I have 0 on the right. So to add 14 more to the left-hand side. Then I look at the left-hand side, I've got 6 and -1. So this has actually become 7, right? That's going to become 7. Since it becomes 7, I can go back to my periodic table. And look, it's no longer carbon. It is now nitrogen because I've gone up 1 from 6 to 7, right? So now it is nitrogen. All right. Okay, so now it's nitrogen. And what that means is that the 1 neutron turned into a proton, right? So neutrons, because you think about it, I still have 14, right? If we think about this as far as neutrons and protons, right? This one is 8 neutrons, 6 protons, and this is 7 neutrons and 7 protons, right? Which means that we had a neutron turn into a proton. Okay, now we're going to do beta positive decay. All right, so same idea here, right? If I look at my nucleon, my 14, I have 14 left, I need 14 on the right, so I still put 14 here. But then I look at my charge. I've got 6 on the left, and I've got a 1 here. So how many more do I need to add? Well, I have to add 5. So now the number of protons is 5. And if I check out my thing, that tells me that it's now boron. It's gone from carbon down to boron. So I use a capital B here. All right. This is why the beta particle, you always put a little line at the end, especially if you have boron, but you won't see that very often because carbon doesn't really do beta decay that often. All right. And you can do the same idea. We can consider, okay, well, this was 8 neutrons, 6 protons. And this is going to be 9 neutrons and 5 protons, which means a proton turned into a neutron. That's beta positive decay. All right, so that's kind of that question there for beta positive and beta negative decay. All right, the next, this is just the pause video here, all that kind of stuff. All right, so the next is gamma decay. All right, gamma decay is kind of the idea where we have, it's usually a new nuclei is formed. After we go through kind of a alpha decay or something, we get a new nuclei formed, but that nuclei is not quite perfect yet, and then it's going to transition and switch and move into a more perfect location. So it's going from a high energy state to a low energy state, which is going to give off a gamma ray. All right. Okay. And so basically what it is that since remember that example where I said we have a whole bunch of nuclei, right? I'm gonna have to move over here. The best example I think of. So we have our kind of our boundary, right? This is our boundary. Inside that boundary, strong nuclear force takes over. Outside, the electrostatic force takes over. And we've got, I'm gonna draw these extra, and we've got our things like this, right? Okay, and so I'm drawing them big. We've got some positives. Okay, and I've got 9. And so what's going to happen is we're going to go through alpha decay. So alpha decay tells me that I'm going to take these ones and we're going to push them out. When we do that, what happens is for just moments, not a very long time, for just a moment in time, we have something that looks like this. Yeah, so it looks like this, right? Where I've got kind of this concept. Now these things are going to move in, right? But when they move in, right, these are going to move in to the center. When they move in, they're going from what's considered a high energy state, so the farther away from the center, they're higher energy, to a lower. So they're going to move in, and when they move in and they come to that center piece, right, when they come to that center piece, they're going from high energy to low energy. The same as an electron, when it goes from high energy to low energy, it's got to release energy. And so when it does this, it releases our gamma ray. Okay, it's our photon, right? This is our gamma ray or photon kind of idea. And so when we have this happen, it's the rearrangement of the nuclei, right? So I've oversimplified this, right? Generally, instead of having 8 nuclei, we've got like 200, right? And the 200, when you lose an alpha, they don't move this far. This is a huge energy transition. They're just going to move slightly from, a little one here to a little bit more in. Okay, and so we give off these gamma rays, and so usually a gamma ray is basically the result of alpha or beta particles happening, changing, right? Okay, and so the nuclei, right, and so this was alpha decay, this step. Okay, and this is gamma decay. Right, so from 1 to 2 is alpha decay, from 2 to 3 is gamma. So when we have gamma decay, we notice that we have 4 nuclei here, and I still have 4 nuclei. And I have 3 protons and 3 protons. So the actual change, right, the actual change doesn't really happen. I have A and it stays as A. I have Z and it stays as Z. The nuclei doesn't change. We just emit it, right? So it goes from excited barium to a less excited barium. That's all that happens, and it gives off a gamma quanton, photon, okay, high energy little bugger. All right, and this is kind of what it looks like here. We have radioactive decay series, and so we'll have an alpha decay. Okay, so what we're starting with here is we have uranium-92, or uranium-238, unstable. Okay, it's unstable because it's outside that strong nuclear force, so it's going to decay alpha. Then it can't really decay alpha again because this element doesn't really exist, right? We don't have what's called 230 radon, a radium, right? So it doesn't exist. And so what we'll do is we'll have some beta decay will happen to get us over to here, and then we'll start doing alpha, 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 alpha. And then sometimes they beta, sometimes they alpha, they can beta, and eventually what it's going to do is going to get closer to, mercury, titanium, right? This kind of stuff, because these are much better, much more stable. Okay, and so that's kind of how decay works. Is sometimes we go down the periodic table, but then we go back up, then we go down, 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 and back up. We can go down and back up, and it all kind of depends on what's happening, as far as stability and all that kind of stuff. All right. So yeah, that's kind of the idea. Now remember, each time we do one of these, or every couple of these, there is going to be some kind of excited nuclei that needs to be rearranged. And so, for every step, or every second step, or every third step, we're going to release a gamma ray as well, right? So we have alpha decay and then a beta, where the two of them combine. Well, there's 2 excited, so then it has to, release a gamma and rearrange and work its way down. Now, this doesn't just happen bang, 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 bang. This can happen over time, right? We can do lots of the first ones stop here for a long time, then it'll decay again. And there's kind of whole sorts of stuff there. So, okay, this is the more interesting part, I guess, of nuclear radiation. So, nuclear radiation, we can get radiation sickness. So, radiation can ionize cells and can kill cells, especially in the blood, and leads to nausea, vomiting, diarrhea. Okay, dying from radiation sickness is very awful. Your body just kind of stops functioning. Like all those things you learned in bio just stop happening. Okay, all the reactions, and so when you need certain elements, and like you learn in bio, there's certain elements or certain things, this and that, and they're very specific. When you get hit with radiation, those things are no longer that thing. They change, and that's bad, right? So when you get a gamma ray comes in and hits a nice little blood cell, this blood cell is no longer going to be a blood cell. It's going to be something else. It's going to mutate. Okay. We can also get high energy photons can alter the DNA. So like inside the DNA, those photons can get in there and cause mutations. Okay, and that's super bad as well, which gives you kind of cancer, genetic mutations, all that sort of stuff. So okay, and generally you're gonna see a lot more with gamma rays because it's got higher energy. Okay, and how far it can penetrate in, right? Okay, so the main one you've ever seen or heard of is Chernobyl. Chernobyl was bad. Okay, it can measure in grays. Radiation exposure is measured in grays. You don't have to know this. Is just for interest sake, or sievents. Okay, basically the idea is that 6 sievents in a short time is usually fatal, and the average person goes through 5 times 10 to the negative 3. You know, an X-ray dental is about 73 times 10 to the negative, what's you, negative 6 Siemens, right? So it's not very much. You're going to get radiation in your body, but usually what happens is when you get radiation or you get a cell that's been destroyed, your body just rejects it, destroys it itself. Your body finds them and destroys them, right? Well, then there's Chernobyl. So, April 26, 1986, okay, basically there was a steam explosion, blew the roof of the reactor off, sending radiation to the air, up, down, everything. And then they had a massive fire, which caused more radiation. Not good. Okay. All bad. All right. And so Chernobyl, basically, radiation levels were estimated to be 0.56 grays per second, which is about 200 grays per hour. And lethal doses are around 5 grays in 5 hours. So you were getting 200 grays per hour was kind of the estimation, and a lethal dose is 5 over 5 hours, right? So in some areas, the unprotected workers, even if you were wearing protection, right, these gamma rays are so powerful that they receive fatal doses in several minutes, right? They didn't die in several minutes. They just, their body was going to die, okay? And the reason that they didn't realize how dangerous it was, the reason why they didn't get out of there immediately, is that they had the things that measure radiation, okay, can only measure up to 0.001 grays per second. And so when it got up to that measurement, it just stopped. It just said that. Like, there is radiation. And this is not a super dangerous level. This is a very dangerous level, right? And so if your measuring device says, well, this gets to this, you don't know that, you know it's higher than this, but you don't know how much higher. You don't know, realize it's that much higher. So most of the people who were there were dead within 3 weeks from radiation poisoning. And this led to a lot of problems. We have long-term problems, as in we have mutations and cancer happening. People who lived within hundreds of miles for the next 50, 60 years. You know, that's kind of, that's been bad, that part. The Chernobyl, they went and they put a giant cap of concrete on it to keep the radiation in. It's still leaking out and there's stuff like that. But there's more effects as well, right? For example, once Chernobyl happened, everyone kind of turned against nuclear power. Even though nuclear power can be safe, it is the most dangerous version of power. But it's also the most efficient, which we'll learn in a later on thing, is that compared to like gasoline, nuclear power is like way, way, way more efficient per kilogram kind of idea. So, all right, so you're going to get into practice problem 6 to 11. You may need to use your periodic table to solve some of those questions, and you're going to read questions 5 in the tuition guide and do 16.3. Next chunk shouldn't be too bad. Thanks.